About Netlist. We will look into looking into concept of standard cells, and then we will start looking into the timing of it. Okay, so let's get started. So what is it? I just sketch. Let's look into this one. Yeah. So look into this picture, and you can see that we have few cells or few gates connected with each other. So we have 3 input ports and 1 output port. Then from A goes into a flip-flop D. Output Q is connected to inverter, then an AND gate and flip-flop. I'm showing that this database is routed, so any horizontal metal is red, vertical metal is green, and then we have these blue are the VS. So I created myself this netlist. Hopefully, I might have some syntax issues, but the main thing is this netlist is in Verilog format. So if you look at, you have A, B, clock, 3 inputs. See, I missed already O. So the syntax is that on the last one, we have this. I can close something like that. Okay, exact syntax you can do Google it. You can find it later on during the training. I'll show you an actual netlist too. So not a problem. But the key thing is, okay, you have a port declaration, and then you have instances of these cells. So FF has an instance. So this FF is the name of this cell. Yeah, or in other words, if I have a Verilog model of this flip-flop, there will be a module called FF. Okay, and then FF1, I'm instantiating that one here. And this cell has 3 pins. It has clock, it has D, and it has Q. And each of them I am connecting based on my connection in the netlist. So you can see that clock goes here, A directly connected, and Q is connected to N1. So I'm calling this wire between an output pin and an input pin is called a net. So N1 is a net which makes a connection, and you can see that I put N1 here, which connects to the A. So these nets are anytime connection. For even here, from A we have a connection to D, there is a wire there. Now, in most cases, this can come from based on how RTL was written, of input RTL that went to. By the way, this netlist was generated from which stage? From synthesis stage. So it's generated from synthesis stage, and then comes each stage after synthesis modifies the netlist. For example, in placement, it looks at, okay, where this flip-flop, this AND gate is placed, and look at the timing path, it might put 2 inverters. Sorry, there's already, if this is coming from RTL, so it means there is an inversion, it has to put another 2 inverter, or it might put a buffer there. So netlist modification is done in placement. Then in CTS is going to put buffer trees on it. So that is the modification. Router can also modify, and they can play with the size of these cells. We'll talk about the size in a second. But anyway, this netlist was created from RTL first time during synthesis. So we have ports and we have nets. Nets, you understood that, right? So even though this net is not called anything, it's still A, because it's connected to this port. This whole net is, if somebody didn't create a separate net in the RTL, this will still be CLK by default. All right, so you have nets everywhere. And then you have, these are called what? Leaf cells. Why these are leaves? The leaf is the leaf of it. There is no further branch into that. That is really the last one. So if we have, for example, let's say this is another module, and inside there is another module, inside there's another. So now we have hierarchical cells. Those are hierarchies. Remember, in I think one of the previous videos we discussed, those are hierarchies because each hierarchy then has further cells. But these cells that you see here, these are the leaf cells. or these are the, and they are also called standard cells or gates. So that's one thing. So these are leaf cells, and then what is the reference cells? So this is the instance. We call it how many instances we have a design. So this is an instance is FF1. I didn't mention here, but FF1. But actual module that is FF. That actual module whose copy we are creating here. But it can have multiple. So this is another copy of the same cell. But here is called FF2, which I don't have in the netlist, but oops. FF2, that's the instance name. So I want to make sure that everybody is familiar with these names, okay? So we have instances and we have reference cells. So then we have leaf pins. These pins are leaf pins, but there are also hierarchical pins. So for example, if you have a bigger module, so let's keep going that way. If we have this module, and inside that we have another, let's say we have these gates there inside, and then this is our top level. So then these pins of this cell, eventually they are connected to the gates, right? So in this case, these pins are hierarchical pins, and these are the leaf pins. The ultimate leaf cells pins are called leaf pins. Is that clear? Yeah, ports we already know. All right, so where all these cells are defined, right? When RTL given to synthesis tool picks, translates that RTL into gates. So where are these gates defined? Well, I mean, definition, somewhere somebody need to mention those, that okay, here are the gates that you can use. Here are the pins of those gates. Here is the functionality of those gates. And later on we will talk about here is the timing of those gates. Right? Where is that information? That information is in standard cell library. Okay, you understand that? Now, in physical design, our smallest unit is these cells. These cells are made of further what? Transistors, right? Inverter has how many transistors? 2. Next we will look into CMOS. We will do a revision of basic CMOS so that you can look into the current, the resistance, the capacitance, and all those concepts, important concepts, and the timing concepts, the concept of the delay and the transition time and all that. We will go through quickly, not too much detail. We will look into transistors, behavior, quickly, how a transistor connected together to make inverters and buffers and some other gates. But right now, if you look at the smallest block that our tools place around synthesis to, they deal with, those are the those standard cell blocks. And these standard cells are already layout ready, and their timing information is also ready. And that timing information is present in the timing libraries. And similarly, there are layout libraries where their layout information is available. For example, what metal this A is, where in that bounding box A is located, what is the total bounding box, what is the height, width of that cell. That information is in the layout library. Timing information, we will get to that. But in generally, what kind of cells we have? What kind of gates we have? We have combinational gates, we have sequential gates. Okay, output of the you know that, okay, combinational cells only depends on the inputs. But in the sequential case, your output depends on previous input. Okay, that is called a flip-flop or a latch. There is a storage element there. It can remember for certain time its previous value. The previous value stays there. It only changes on a rise edge of the clock or fall edge of the clock. If rise doesn't come, the previous information which was sitting there is still stored, right? So that next stage can perform some action. So examples of the combinational gates are, okay, inverters, and NAND, and OR. Here you see that there's an and this kind of in the standard cell library, we can also have this as a complex gate, but we can have this gate. What about this one? What kind of gate is it? This is incorrect. I intentionally added that. So you see that we can have two cells driving one net. That cannot happen. So I intentionally put there. So this is incorrect, right? But generally, now in this case, you can have this scenario where one cell is driving multiple inputs, but you cannot have this one. You need to put tri-state buffer here. Only one of them can drive this one. The other will be in high impedance state. All right, so the other point I want to mention that in standard cell library, you can have each of these cells. There will be different sizes of it. You can have a inverter, smaller inverter. You can have bigger, 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 bigger. A lot of variation of those. Sometime maybe tens of inverters, tens of AND gates, tens of NAND gates, or sometimes even more, depends on that particular technology. Who provides that standard cell library? Typically, your fab. For example, TSMC is going to provide that. Intel has its own fab, so they have internally generated that standard cell library. And what is mean by when I say bigger, bigger, bigger? Means the transistor, and next we will look into it, the transistor has a bigger width. And we will look next week into is what bigger width does. But bigger width generally means it's going to be faster. All right. So similarly, we're not going to talk about latches. This is an example of a latch. Maybe at the end we will do a couple of lectures on latches. But right now, let's focus on flip-flops. And another example of the sequential cell is what? An SRAM. Yes, it's also a sequential cell because it also gets a clock, and when address comes here, certain data goes out. So on the edge of the clock, right? Similarly, each of these signals it's also like a D pin of a flip-flop. So this is where the timing information or timing path ends. These are endpoints. So each pin of an SRAM is also, each input pin of an SRAM is also kind of is a sequential input pin. It's like a flip-flop D pin. All right. Okay, so let's quickly talk about the timing arcs. Probably the last thing. So timing arc is, if there is a transition here, a signal going from 0 to 1, it goes from here to here, right? That's the only way. From input, output is function of input. So it will be like flipped because it's inverter. So what about this one? It has how many timing arcs? This input can go here and this input can go here. I mean, a change at input, depending upon how is the other logic. I mean, on AND gate, you know that one of the input is 0, it will be 0. So how these two, this change of transition from here can go here, or from here can go here. So this is one timing arc, this is another timing arc. How many timing arcs are here? There are 3 timing arcs. 1, 2, 3. Keep in mind, these are not timing paths. So this is the timing, how a change on one of the inputs can go to the outputs. And it can, if you look into truth table 0, 1, 0, 1, you will see 1 was 0, the output was 0. It was 1. When input go to 1, output will go 1 because this is still 1. So 0 to 1 transition went to output. Similarly, for if this is 1, this makes 0, 1 or 1, 0, this will change. So in a way, we can say that, okay, this transition is moving from this input to this output. So timing arcs, these are timing arcs. These are within the cell. So it's a timing arcs. Timing arcs can be outside. Those are wire timing arcs. We will look in next time. But what about flip-flop? What kind of timing arcs it has? Can you guess? So it has a timing arc from clock to output, from here to here. But it doesn't have D to Q. There's no timing arc. Why? Because if if you know, this flip-flop inside has two latches. One latch is active at one time. So, and this edge is the time when from one latch goes in the blocking state, other goes in the transparent state. So D never has a direct path to Q. There is an internal node where D goes, so that's where the path is from in D to that internal node Q. But basically, it's really the edge of the clock that determines that timing arc when D goes to output. So you have a timing arc from here to here. But in the case of flip-flop, you have some additional timing arcs. What are those? You have a timing arc from clock to D. What is that called? That is your setup timing arc. This time, as you know the definition, we will look further into detail. This is assuming rise edge flip-flop. The time that D needs to be stable before the rising edge of the clock so that during this time it doesn't change. That time, that yellow duration, this horizontal, is called setup time. So there will be a timing arc of D with respect to clock, and that will be setup timing arc. Similarly, enable pin will also have the setup timing arc. Reset will also have a setup timing arc. Okay, so your launch, when flip-flop is used as on the launching side, then this is the edge timing arc. And when it's on, when flip-flop is capturing, then this is the timing arc. All right, let's finish it here. Hope that was not too basic. If please let me know your thoughts as I'm not seeing the class directly, not seeing your faces. It's very hard for me to see if I'm going too basic or this is good enough for you. I'm sure it will be not basic for some of you out there. I just wanted to make sure that I take along everybody. All right, that's it for now. I will see you in another video this week.